This is Berkeley, and he's going to tell us a bit about semantic program alignment for equivalence checking.
Thank you. Glad you could all make it this morning. I'm excited to present the work I've done over the last few years, and I'll jump right in with one of my favorite examples. So this is the string length function that you all know and love. It's very simple, but if you actually look in glibc and see how string len might be implemented, you could see this. It's a vectorized implementation. It has a warm-up loop. It reads out 8 bytes at a time, and does an H-way branching if statement. And it turns out that these two programs are equivalent, and provably so. And we'll show you how to do that. So equivalence checking is this problem of taking two functions or procedures and proving that they are equivalent. We want to show that they perform the same computation. So key applications include checking the correctness of optimizations. You can compile some code with a compiler at the -0 and -3 optimization levels and check you get the same binaries. You can enable speculative optimizations. For example, you may have a super optimizer, which gives you faster programs that might not be correct, and so you can use an equivalence checker to verify them. You can also check handwritten optimizations, like the glibc example. And we are specifically interested in black box equivalence checking. So here, we don't know what compilers generated our binaries. We're doing everything at the assembly level. These binaries could be handwritten, and they could come from any programming language. We try to be agnostic to that as much as possible, and we don't have any type information, no information from the compiler. And we say that two programs are equivalent if when you run them on the same input, one of two things happens. Either they both terminate in the same output state, or they both fail in some way or another. So in the past, a common technique is to take two programs that you want to check equivalence for and construct a product program, and then use verification techniques for a single program to check assertions. So one way is to sequentially compose these two programs. So here we have some loop iterating over a basic block and another one. And you can create a product program where you simply have both of those loops one after the other. And you want to check this assertion that the two outputs are equal. But this is very hard to do because you need to either somehow summarize these two while loops, which could be very difficult, or do some other kind of general verification technique. And so this is usually not tractable. So a simplifying observation is that many times when you're trying to prove equivalence, but not always, you will find that these two loops will execute the same number of iterations. So you can imagine that these are execution traces, and you might observe that after executing one iteration of each loop, there is some relationship between the states of these two programs that you can observe. And you might find that this relationship holds going into the future. So you can come up with some sort of candidate invariant, which you can then use to facilitate an inductive proof of equivalence. So this looks like so. You create a product program, and then instead of the loop, you are actually executing the basic blocks from both of the original programs. And on each iteration, you're asserting that some invariant holds, and then doing a proof of equivalence can be quite straightforward depending on the situation. So here's a concrete example. Here we have this function f, and it's summing even numbers. And then in program G, there's a strength reduction optimization applied. So in program G, on each iteration, we are incrementing j by 2, whereas in the original program, we're multiplying I by 2. So you can compose these two programs using this very syntactic construction. You see that we have essentially a main loop with a preamble, and the preamble and main loop code is essentially copied from the two original programs. And then you can come up with invariants that assert the relationship between these variables. So here and throughout the talk, we'll use primes to represent variables from the second program G, and the lack of primes suggests a variable from F. So there are a number of limitations of this previous work. So if you have a different number of loop iterations, you're not going to be able to succeed. If you can't find a syntactic correspondence between the two programs, like if one program has another loop that the other one doesn't have, it'll fail. And depending on the specific syntactic choices you make, you could create a harder problem than necessary. So in particular, some optimizations that these techniques can't handle include loop unrolling, loop peeling, and vectorization. Some other ideas include unrolling or unpeeling a loop before applying a syntactic technique, but this only applies for very specific optimizations, and it's in practice very hard to predict how a vectorizer might unroll or unpeel a loop ahead of time. Other work searches for a product program, but the most recent work, the search isn't efficient and it often can't handle many of the vectorization and loop unrolling benchmarks that we're interested in. So this is a running example which illustrates many of the challenges we want to overcome. So here we have a program F, and it is iterating over an array of integers and flipping the bits of each one. Program G has a vectorized loop where it's going to flip the bits of two integers at a time. And then beforehand, if it checks if the length of the array is even or odd. And if it is odd, then it flips the bits of the first array element in advance. So we have a data-driven solution. The idea is that we run these programs on concrete inputs, and we see these execution traces. And we come up with a semantic way of aligning these execution traces to find corresponding control flow paths between the two programs. And then we use that to go and build a product program. And the key idea in doing this is this idea of an alignment predicate. The alignment predicate is a weak invariant that helps us find corresponding paths, even if we don't have any kind of syntactic correspondence between these two programs a priori. And once we have the product program, we can use existing techniques to complete the proof. So we represent our product program as an automaton. This automaton can also be thought of, in a sense, like a control flow graph, where the edges on the basic blocks are labeled by the basic blocks of the original programs. So the big picture is that we're going to guess an alignment predicate. We're going to use that to come up with some correspondence between the concrete execution traces of these two programs. And then use that to build this representation of the product program, this program alignment automaton. And then we are going to learn some candidate invariants for this program and then check the proof obligations. And then what happens is that we try this for an alignment predicate. If it succeeds, then we're done. If not, we try it on a different alignment predicate. So I'll jump right into that. So here are the functions f and g. This is a trace of f where each row is represents the execution of one basic block, and similarly for g. And these are the control flow graphs of both functions. So you might ask, what's a good way to align these two programs? And for this particular pair of examples, you'll notice that function f on each iteration dereferences this address array plus 4 times the array index. And function g dereferences its copy of the array index. So one guess for an alignment predicate is that you want array plus 4i to be equal to array in program g. And if you do this, we can then pair up states in this trace. So if you'll look here in this row, we have that I equals 1 and array is 100,000. And so this entry in the trace can be paired with this other entry where array prime is 100,004. So this correspondence between these traces isn't one-to-one. In fact, it's many-to-many in general, but we're going to use it in a meaningful way. So to actually come up with the alignment predicates, we do something that's very simple, which I'm sure can be improved on. We essentially guess alignment predicates just from a predetermined space. And it's essentially linear combinations of up to 2 registers or program values. There are actually, I think, some underlying reasons why this space works well for x86-64 programs, and we talk about it in the paper, but there are also, I think, many better things you can do than what we have. So once we actually have the alignment predicate, and we can go and find these corresponding pairs of paths. So what you can do is you can take two of these edges that we've drawn in, and you can really pick any two that you want ultimately. And this will delimit some path through program F and some other path through program G. And if you look at what these are doing, so this path AB, that corresponds to entering the loop and executing one iteration. Path A prime in program G corresponds to entering this guarded block and flipping the bits of the first array element, which is exactly what we would expect. And if you pick another two, we can find that two executions of the loop of F corresponds to one execution of the loop of G. And I'm recording these pairs of corresponding paths down here. And we can also find that the exits correspond to each other. So now we can use these paths to go and build the automaton. So we start by creating a start node, and then for each of these corresponding pairs, we simply add that in to the automata and create additional nodes as needed. We can go through, and you'll notice that now we have a product program that has some loop, it has an entry and an exit, but actually this product program doesn't capture the behavior of the two original programs. So in particular, program G, it had this case where the guarded block was skipped, which corresponds to this path B prime, and you don't find B prime in this automaton. And that's because we built this automaton using a concrete execution trace where the input length was odd. But if you were also to do this again with an additional trace where the length was even, you would find another corresponding pair, AB prime. So now, at this point, we have a complete product program, and we can essentially leverage existing techniques to prove its correctness. So we can run the product program on our concrete data. We can collect all data points at a certain node, and then we can learn some candidate invariants. So we need to go and check that these are true. We use a fixed point process to throw out conjuncts that don't hold. So some might be true while others aren't. We assume at the beginning that you have some equality of inputs, and at the end we want to prove that the heap states are equal. So the big picture is now that we've learned these candidate invariants, and you can go ahead and check your proof obligations. So our proof obligations basically say that your invariants hold, and you also need to show that there are no missing edges in your program alignment automaton, that it's a sound approximation of both of your original programs. So if we were missing that edge that came from the even trace, then your proof obligations would fail. And you also want to show that the invariant at the final state implies the equality of outputs. So in the paper, we have this theorem. We show that if the proof obligations hold for the program alignment automaton, the procedures are equivalent, and the proof is by induction. So this is the big picture of what we're doing. We evaluated our technique on functions from the test suite for vectorizing compilers. We had 28 functions, which we compiled with GCC and Clang at the 01 and 03 optimization levels. These benchmarks had a lot of vectorization. Many had loop unrolling and loop peeling. Some of these also had warm-up and cool-down loops once they were optimized. We had a little bit of floating point, and we had an example of a doubly nested loop in there. Often these benchmarks are traversing over arrays, and there's a whole bunch of other optimizations that GCC and LLVM are performing. It's like hard for us to actually go through and enumerate all of them, but for example, we see that they have transformed branch conditions. So there's a lot of different things that we're able to verify. We used Z3 and CVC4 solvers to discharge the proof obligations. We have a lot of proof obligations. We have a lot of conjuncts in these invariants. So we actually discharged these in parallel on a number of machines. And we find that we can verify just about all of them. The one holdout is we had timeouts from the SMT solver. And in fact, we find that if we refactor our constraint generation, we can get this last one to succeed, but then another one will fail for a timeout. So there's a lot of finickiness in creating those inputs. The semantic program alignment part works great. It was able to take care of the Stirlen example. What we were able to show is that in the warm-up loop, there's essentially a one-to-one correspondence between executions of this loop and the original one. There's an 8-to-1 relationship between executions of this loop and this one. And then in our program alignment automaton, there's 8 additional edges, one for each of these if statements. So it'll essentially say that the path which begins at this loop and goes through the 4th if statement corresponds to taking 4 iterations of this loop and exiting. So this captures some of the disjunctive properties of this program. So there are some things we can't do. So we can't do loop fusion. We can't do loop splitting. Basically, anytime you are reordering memory dereferences over an unbounded array, we're going to have trouble with that. So in conclusion, the key idea here is we're using this weak invariant, which we're calling an alignment predicate, and this bootstraps the creation of this product program. And once you have the product program, it's very doable to go and learn a stronger invariant that you'll actually use to do the proof. And then we can handle real optimizations performed by compilers today. Any questions?
Leonard Beringer, nice. I assume this generalizes in principle to more than 2 copies of a program. You could construct automata with sort of more than 2 executions conceptually. But I'm wondering, can you generalize it to other relations than equality in the pre and post conditions?
I think so. There are some relations that I think are easier to do than others. I think if you have some sense that the control flow needs to match, you can certainly prove other kinds of relationships, but I think it'll require some investigation to figure out exactly which ones you can and can't do.
So very cool. So sometimes full binary equivalence is stronger than you care about. So a toy example is if you have pad bytes in your struct, you can mess with them and it doesn't matter. Are there non-toy examples people care about? Is this future work? Is this worth looking into?
Are there non-toy examples for full binary equivalence checking?
Where binary equivalence is too strong.
Yeah, there are definitely a lot of examples for sure.
But you need some outside information from the source, because you're at the binary level. Mm-hmm. You don't. I assume the way you set this up, you don't have that information.
Correct. Yeah.
Right. Do you think there would be practical ways to get that information into your tool, like these bytes don't matter, or the return result isn't being used, it's only for the side of different things like that?
Yeah, sure. So we can always, if you can just provide more information about what bytes you don't care about, then we could handle that. Yeah.
All right, thank you for your time. That's a beautiful talk.